Good morning, dear colleagues. Today we will continue our series of seminars where we are solving different tasks for radiochemistry, and today we will calculate different doses from different sources of alpha, beta, and gamma radiation. And today it will be like introductory seminar, and in later seminars we will continue to solve this task. So, and the first task is that we have a point source of thallium 204 with a known activity, and we have to calculate the flux density of these particles. It is beta emitting radionuclide, so we have to calculate the flux density of the beta particles from this point source, and also we will need to determine the particle fluence and the energy fluence that we get in 1 hour, and we know all the parameters that we will need. So let's start to solve our task. Again, we have a point source of the energy or beta particles, and we should remember that the radiation is emitted not in one direction. It's not just a linear ray, but irradiation goes in all directions, and thus it forms a sphere so with the radius that is equal to our distance from our point source to the our observer or to our detector or to whatever. So what is the flux density? The flux density is just the number of particles that is going through some area, surface area, in some period of time. So if it would be just a parallel flux of the particles, and we know some area of the surface, then and we know the number of particles, so the density flux will be simply the number of particles divided by this surface area and divided by time. So per second or per hour or per minute or other times. Now, when we look at this equation, we see that we need number of particles that are emitted. We know the activity, but it will be not equal to our number of particles, and we will see why it is so. And also, we will need some surface area. And as I said you previously, that radiation is going like a sphere, and thus we have to calculate the surface area of this sphere. And we know that it is simply 4 pi squared, and that's it. So we know the surface of our sphere. Okay. Now we need to calculate the number of particles that are going through this surface area. How to calculate it? Of course, we know the activity of our source, of our point source. That means that we know, so activity is just, we can say that it's a number of beta particles that are emitted in some time. But this point source is located not in vacuum but in air, and thus part of the beta particles will be absorbed by the air. So we have to calculate the attenuation coefficient for beta particles. In this case, we have quite a short distance from our point source, and we can see that maximum range of our beta particles is quite long. We can recalculate it in centimeters. So let's do it. So we will calculate the linear distance or linear maximum range for our beta particles. It will be simply maximum range divided by the density of the material where beta particles are going through. And for us, it is air, and we know the density of air that is equal to 1.29 milligrams per cubic centimeter. So we divide this maximum range, milligram per squared centimeter, and we divide it with density of air. So we transform the gram per cubic centimeter to milligram per cubic centimeter, and thus something like 223 centimeters. So you can see that for thallium-204, the maximum range of beta particles is more than 2 meters in air. And in this case, we can use the equation for attenuation coefficient like this. Attenuation coefficient will be simply the exponent with the degree minus attenuation coefficient, mass attenuation coefficient multiplied by the distance. And let's calculate it. So the attenuation coefficient will be, in this case, exponent minus 20.5 squared centimeters per gram. Our distance is 50 centimeters, and we have to multiply it by the density of air, and in this case we will take back grams. And so 0.267, let's say, for attenuation coefficient. Attenuation coefficient means that this part of beta particles will go through our air layer, and thus the whole number of particles, we should multiply just the activity with the attenuation coefficient. So the number of beta particles that are going through the surface area of our sphere will be simply the activity multiplied by the attenuation coefficient and by time. So thus, when we calculate the flux density, it will be our activity multiplied by the attenuation coefficient divided by the surface area of our sphere. So like this. So let's put all the numbers that we have for our task. So it is 2.4 megabecquerels, so it's mega 10 to 6. Attenuation coefficient 0.267 and multiplied by 4p. And let's take our distance just in centimeters. We will not need to calculate it in meters. So this will be 50 squared. And 20.4 particles per squared centimeter. Okay. Now we need to calculate the fluence. And what is the fluence? The fluence is simply the number of particles divided by the surface area. So it's the whole number of particles that go through the surface area for a certain time. We know the flux density, and now we can calculate our fluence simply by multiplying the flux density and time. So we have 1 hour. Sorry, there is also a second. Yeah, second minus 1. Because we have activity, it is particles per second. Yeah. And thus we simply multiply 20.4 by 1 hour. 1 hour, it is 3,600 seconds. So we will obtain 73,440 particles per squared centimeter. Okay. And what about the energy? We know the energy, the maximum energy of beta particles that are emitted by our point source, by our thallium-204, and thus we can calculate the energy fluence by multiplication. Let's call it fluence with index E, energy. So it is our flux, let's say, particles multiplied by the energy, maximum energy of our beta particles, but it's maximum energy. And we have to remember that the average energy of beta particles is equal to 0.4 of our maximum energy. So we just multiplied it also with 0.4. And we will obtain, so it is something like 2.2 to 4, 10 to 7. It's kilo electron volts. And we can recalculate it in joule, for example. Also, we have to remember that 1 electron volt is equal to 1.6 to 10 to minus 19 joule. So we multiplied our 10 to, so as far as kilo electron volts, I will convert it just in electron volts, and we multiplied it with 1.6 10 to minus 19, so joule per electron volt, and it will be 3.6 10 to minus 9 joule in 1 hour. So this energy, this is the fluence of energy at distance of 50 centimeters from our point source. We will see how we will use it, how we can use it to calculate doses. So this part is very important to understand the further calculations. So first of all, it is that we have a sphere for our radiation that released from the point source. and we have to take into account the surface area of this sphere. So the next our task is to compare the energy fluxes that are created by beta particles and gamma radiation in air, again at a distance of 50 centimeters from the point source. And this is the diagram that shows us the energy of particles that are created, that are released, and the yield of these particles. And there is some additional information about the linear attenuation coefficients for gamma quanta and the mass attenuation coefficients for our beta particles with these maximum energies. So let's try to solve this task. Again, what is the flux densities? We can write it again as so the flux density is equal to number of particles divided by surface area in time. But as far as we need to calculate the energy fluxes, that means that we simply multiply it by the energy of our particles. For beta particles, the average energy is equal to 0.4 multiplied by the maximum energy, and for gamma quanta is simply the energy of gamma quanta. But we see that there are two kinds of beta particles and two kinds of gamma quanta. In this case, the total energy flux will be, so the total energy flux will be just a sum of our number of particles multiplied by the energy, but the surface area will be the same for all of them. And we can calculate the number of particles like in the previous case, taking into account the activity of our point source. So again, for beta particles, we have to take into account the attenuation or absorption of the beta particles by air. So let's calculate the attenuation, let's say 1, it will be for beta particles with energy 1.2 mega electron volts, and second factor will be for energy 2.2 mega electron volts. Also, what we should do, then we calculate the number of particles and we calculate it from the activity of our source. It will be the activity of our source, and we have to summarize the yield of each kind of beta particles or gamma quanta multiplied by the energy of these particles. And also, as far as there is attenuation, we have to multiply it by attenuation coefficient, and then divide it all of this by the surface area of our sphere. Okay, so let's calculate the attenuation coefficient for beta particles with energy 1.2 mega electron volt. We will take 10 to 1, it is mu, multiplied by the distance, 50 centimeters. And we remember that the density of air is 0.00129 gram per cubic centimeter. And thus, we will obtain 0.52 for the first sort of beta particles, and for the second is minus 4.6. Distance is the same, the density of air is the same. And it is not surprising that for particles with higher energy, the attenuation coefficient will be higher. That means that in this case only 52% of all beta particles will go through the air of with thickness of 50 centimeter, and in this case it will be 74% of beta particles with the maximum energy of 2.2. And let's calculate now the energy flux density for beta particles, because we have to compare the energy flux densities for beta and for gamma radiation. Let's calculate it for beta. So it will be activity that we don't know, and it is not required, because we will take just the ratio between energy flux for beta particles and gamma radiation, and this activity will be simply deleted. So we multiplied it by the sum of, so for 1.2 mega electron volts, we see that the yield or probability of or the release of these particles is 0.7. We multiplied it by the average energy of beta particles, so it is 0.4 multiplied by 1.2, and by the attenuation coefficient, so 0.52. We summarize it with the second sort of beta particles. So the probability of these beta particles will be 30% or 0.3. Again, average energy is 0.4 multiplied by 2.2. And then the attenuation coefficient, 0.74. And we can calculate or not the surface area, because for gamma radiation the surface area will be the same, and thus it will be also annihilate when we will take the ratio between beta particles and gamma radiation. So in this case it will be these brackets 0.37, let's see. What about gamma radiation? We see that linear attenuation coefficient is very small for gamma radiation, and thus the attenuation will be so the absorption will be very small, and the attenuation factor will be close to 1. And we can simply confirm it if we calculate the attenuation coefficient for the weakest gamma ray. In this case it is 0.19 mega electron volts, and for this energy the attenuation coefficient will be simply 0.10 to minus 3 centimeters minus 1, and we multiplied it simply by the distance, linear distance, and we can see that it is 0.992. That means that less than 1% of all gamma radiation, even with this small energy, will be absorbed by air. And you can see that the higher energy of gamma quanta, the lower the linear attenuation coefficient. That means the higher the attenuation factor. That means that if we will put here this number, we will get the number even close to 1. And in this case, we can neglect this absorption of gamma quanta, and we can calculate the energy flux of gamma radiation simply like simply we've taken into account that the attenuation coefficient for gamma radiation is equal to 1. So again, for 1 mega electron volt, the probability is equal to 0.7. We multiplied it with energy of gamma quanta is simply 1. Attenuation coefficient is 1, and in this case we see that 100% of gamma quanta with energy 0.19 mega electron volts will be emitted. Again, the attenuation coefficient is 1, and we divided it by S. So here it's 0.37. Sorry, I forgot to write that it is activity and surface area. Yeah. And in this case, it will be simply 0.7 plus 0.19, so 0.89 activity divided by S. Okay, and thus the ratio between these two numbers will be simply 0.37 divided by 0.89. So it will be 0.416. So, okay. I hope that it is clear how we can calculate the energy fluxes, energy flux densities for the sources of beta and gamma radiation. Let's go further. I will clean this desk again. The next task, we have to calculate the ratio of absorbed dose rates now. So we are moving from just the energy fluxes now to the absorbed dose rates, at least in the air that are created by the beta and gamma radiation released from a point isotropic source of cobalt-60, a quite widely used isotope, radionuclide, at a distance of 10 centimeters from this source. And we have a list of parameters that we will need to solve our task. Again, to calculate the dose rate, we need to know how many particles going from our source to the distance of 10 centimeters, and also we need to know the so-called gamma or Kerma constant for in the case of the gamma radiation. So let's calculate our dose rates that are going from beta particles and gamma rays. To solve this task, let's start with the gamma radiation. In this case, it is quite simple calculation, and we already have this constant for our source. And let's do it. So we need to calculate the dose rate. So it's P, like power. Gamma constant is 84 0.6 attograys, so it is 10 to minus 18 gray, multiplied by squared meters, divided by second and becquerel. We don't know the activity of our source, and it is not so important. And sorry, we divided it simply by the distance from our source. And distance, we can take it as 0.1 meter squared. Thus, it will be simply 84.6 again. It will be 10 to minus 2, that will go here. It will be 10 to minus 16. And now it will be gray per second. And we multiplied it just by the number of activity. Okay, I will check if all the parameters are. Yeah, we need to know, sorry, the maximum range also for beta particles, just to see if our distance is small enough that we can use the exponential form of our attenuation coefficient. So for this energy of beta particles, the maximum distance, we can calculate it as so we know in the table that for energy of 0.3 mega electron volt, the maximum range in milligram per squared centimeter is equal to 76. And for energy of 0.4 mega electron volt, so it's energy of beta particles, the maximum range is equal to 115 milligram per squared centimeter. And we have a maximum energy of beta particles that is equal to 318 kilo electron volts, so it's something in between these two numbers. And we can easily recalculate it as following. We know, so it is our range from 0.3, or let's write it as kilo electron volts, to 400 kilo electron volts. And we know that the maximum range is going, it's like a graph, yeah? Maximum range from 76, and we can assume that it is a linear relationship to 115, and we need to calculate it for 318 kilo electron volts. In this case, we can simply take all this line, divided it by the 100 pieces, so it's 100 pieces. So we can calculate what is the addition to the maximum range per each kilo electron volts. Then we will multiply it, this small addition by 18. And then we will add this small addition to our maximum range for 300 kiloelectron volts. So let's do it. It will be the maximum range for our beta particles with the energy 318 kiloelectron volts will be 76 plus, as I told you, we simply take this line, divided it by 100 pieces, and multiplied it by 18. So let's calculate it. So I got this number, 83 milligram per square centimeter. Okay. As far as it is air, we can recalculate it to the linear distance or linear range, maximum range. It will be maximum range divided by the density. So it will be 83 divided by 1.29 as far as it is in air. And it will be 64 something like 4 centimeters. In this case, 10 centimeters will be less than 0.3 multiplied by the maximum range, and thus we can use the attenuation coefficient that we calculate with this equation. So let's do some step back, because for beta calculations we will need this number. Let's calculate it, okay. So we will take our attenuation coefficient, mass attenuation coefficient, 99.9 centimeters per gram squared centimeters, multiplied by the distance and by the density of air. So it will be 0.306. Okay. Here you can see this equation for dose rate for gamma quanta, and for beta particles it will be quite similar equation. So again, it will be activity divided by the not by the distance but by the surface area of our sphere, and then it will be multiplied by the average energy of our particles, multiplied by the attenuation coefficient, and divided by the maximum range of our particles. And if we will take the energies in mega electron volts, or so we have kilo electron volts, thus we will recalculate the kilo electron volts to joules, or we remember that gray, it is joule per kilo. Yeah. So to recalculate it, we will need this coefficient, because it is not electron volts but kilo electron volts that we will take. So we have all the numbers. Yeah. Okay. So it will be our activity that we don't know, and we will see that it will be simply annihilated. We multiplied it by 0.4 by 318 kiloelectron volts, multiplied by the attenuation coefficient, then divided by 4p r squared. In this case, let's take as far as the maximum range we will take. So we have it in milligram per squared centimeter. We can take it as gram per squared centimeter, and we can take in this case just a centimeter. It will be also neglected, so it will be 10 squared centimeter. And in the case of maximum range, we should to take it in grams, so it will be 0.03 gram per squared centimeter. Okay, and not to forget this coefficient. Yeah. So let's calculate it. Yeah, also, as far as it is grams and it is joule per kilogram, that means that we should also multiply it by 1000. Yeah, also multiplied it by 1000 somewhere here, and also addition of this coefficient. So I got this number 97 10 to minus 14 gray per second. Yeah. And now we simply divide one number by another. So we take this ratio. So it is 5.97 10 to minus 14 divided by this number. So it will be 846 10 to minus 15. And it will be simply 7. So you can see that in this case, even if the maximum range of the beta particles is quite small, it's only 65 centimeters, let's say. So on the distance of 65 centimeters, no beta particles will go to our body, let's say. And all the doses at the distances longer than 65 centimeters will be created by only gamma radiation. But at short distances, the dose rate that is created by beta particles is higher than the dose rate created by the gamma radiation. Okay, let's go further. Okay, now we will talk about our researchers who are working with radiation sources, and we will see if the work conditions are safe or not. This is a very simple task. We know that at working place, the dose rate from some sources of ionizing radiation is equal to 2.3 nanosieverts per second. Is it a lot or not? We will see. And we know that this radiation dose rate is evenly distributed throughout the time, so it is constant with time and constant and the same during the working day. And we need to calculate if these operations are safe or not. So let's do it. First of all, it will be more easier to understand this dose rate if we will convert it not to nanosievert per second, but to, let's say, micro sievert per hour. Let's do it. So we know our dose rate per second, and we will convert it to per hour. It will be nanosievert per second. And in hour, we know that in 1 hour it is 3,600 seconds. Oh, sorry. Seconds per hour. And thus, this dose will be 8,280 microsievert per hour. Oh, sorry, nanosievert, still nanosievert. And let's convert it to microsievert, so it will be simply 8.28 microsievert per hour. In Moscow, for example, the average dose rate that is created by the background radiation is around 0.1 microsievert per hour, so it is something like 80 times higher than the background radiation. But let's see if it is still safe or not. For the personnel that are working with the ionizing radiation sources, the year consists of 1,700 hours. So we are working these hours per year officially. And thus we can calculate the dose that we will obtain with this dose rate. And this number of hours, so it is 8.28 microsievert per hour multiplied by 1,700 hours, and thus it will be 14,000 microsieverts or 14 millisievert per year. Yeah? And we know that the maximum allowed dose for the personnel who are working with ionizing radiation is 20 millisievert per year. So it is allowed. And thus we can see that there is a still safe operation without any shielding. So in this case, we don't need any shielding, any screening to work safely during the whole year with these sources of ionizing radiation. So again, it was quite a simple task, and we will go further to a more complex one. Now we have some specific source of ionizing radiation. Again, it is quite widely used ionization source of cesium-137. it decays to barium 137 metastable, and this metastable state of barium then goes to the ground state and emits gamma radiation with the energy 661 kilo electron volts, and it is widely used for sterilization, for irradiation studies of different materials, etc., etc. So we know that some researcher is working only 2 hours per day, and that's it. There is no other sources of ionizing radiation. So the researcher is working only 2 hours every day with this source of ionizing radiation with quite a high activity. At distance of 30 centimeters, let's say he is working with just bare hands at distance of 30 centimeters. And first we should calculate the daily dose that the researcher can receive if there is no protection. And then, as far as there is already a question that we need some shielding, some lid screen or shield, that means that this dose rate will be higher than it is allowed, but we will see what it will be, and do we need really the LED shielding or not. So let's calculate it, and again in this case it's quite simple. We already have almost all the parameters, so the dose rate again will be simply the activity multiplied by this Kerma constant divided by the distance of our operation. And let's and also it is the dose rate, and to calculate the dose we simply multiplied it by the time of operation, and thus we can again simply calculate the dose that the researcher will get if he will work 2 hours every day with this source of radiation. So we know the activity. It is 394 megabecquerel, so it is 10 to 6 becquerel. We know the Kerma constant for this source. It is you can find it in databases. So it is atto gray, so 10 to minus 18 gray per second, also multiplied by the squared meters and divided by becquerel. Okay. We know time, it is 2 hours, but we need seconds, so we multiplied it by 3.600 seconds, 3,600 seconds. And now divide all this by the distance, and here we have square meters, thus we should convert centimeters to meters. So something like this. Okay, now let's calculate together. So it will be 0.00675, let's say, and it will be gray. Yeah. Let's convert it to milligray. It will be easier, or to, let's say, micro gray. It will be even more easy. So it will be something like this. Micro gray. Okay. But when we talked about the maximum allowed dose, it was 20 millisievert per year. Yeah? Millisievert, not the gray. It is important. From our previous lecture, we remember that this Kerma constant is given for the air conditions. So it is a dose rate that creates in air, that is created in air. Millisievert, it is the dose, equivalent dose, that is created in the human body. And thus, we have to recalculate our dose to equivalent dose with the weighing factor. So our equivalent dose will be weighing factor for radiation multiplied by the dose rate. And also, we have this coefficient 109. That is the difference between the absorption of gamma radiation in air and in tissue. We saw it in our previous lecture. So just remember that when we calculate the dose rate using the Kerma constant, for a certain radionuclide, gamma-emitting radionuclide, we have to convert it to the equivalent dose of this average coefficient. For photon radiation and for beta particles, we remember that the weighing factor is simply equal to 1. Thus, we can simply multiply 109 by 6,745 micrograys, and we will have 735, let's do it like this, microgray. Okay, oh sorry, it's not a microgray already, it is microsievert, because we already converted it. It will be microsievert. Okay. We know that the average, the allowed dose for the research is 20 millisieverts per year. And we know that researchers are working 1,700 hours per year. And thus we can calculate what is the, and also they work 6 hours per day. And thus, when we recalculate all these numbers, we will see that the allowed dose per day will be equal to 72 microsievert per day. And thus, we see that our dose that the researcher can get when he is working with the cesium source within 2 hours is 10 times more than the allowed dose. Thus, it is obvious that we have to use some shielding, and now we will see how to calculate it easily if we have some tables to do this. In principle, if we have a very complex source of ionizing radiation, then we have to perform quite complex calculations, and we will do it next time. And in this task, we will see how it is simple. To calculate the thickness of the lead shielding, we can use such tables. In this table, you can see the energy of gamma radiation expressed in mega electron volts, and also this factor of attenuation that we have to have. Oops. And if you know what is the factor of attenuation you should reach, for example, you should decrease the dose rate by 100 times. Then you take this attenuation factor 100, you find your energy, or if there is no certain energy, you can calculate the this thickness in centimeters. It is the thickness of the lead shielding in centimeters, and thus it is quite easy to find this number. So I remind you that we calculated that the dose that a researcher will receive is equal to 735 microsievert. The allowed dose is 72 microsievert. But also, when we calculate this attenuation factor, we should take the safety coefficient equal to 2. So it is to ensure that the operations with the source of ionizing radiation will be safe in all the cases. So we will always take this coefficient 2 to ensure the safe operations. And then we simply take this ratio, and we will see that it will be equal to 20. And we know that the energy of gamma quanta emitted by the cesium source is 662 kiloelectron volts. And as far as this source is quite widely used, as I told you, there is a certain column for this energy in this table. So we simply find the cross section of 20 and this energy, and we find that it is 3 centimeters. So it is our answer that the thickness of the lead shield is equal to 3 centimeters. So again, it is from one point of view, it is quite simple to calculate this minimum thickness of the lead shielding. Of course, you can take more thicker shielding to ensure more safe operations, but it is the minimum thickness of the lead shielding that you should take to be sure that your operations are safe with this source of ionizing radiation, with this activity at these distances. That is all for today. Next time we will see how to calculate this thickness of lead shielding for the sources of complex sources of ionizing radiation when we will have different energies of gamma quanta, and we will see so how to use our knowledge to ensure the safe operation with to work with the ionizing radiation sources. Okay, that is all. Goodbye and see you next time.